We will continue with topic 2.
Harvest is a mechanical severance. The moment a fruit is separated from its parent plant, the vascular tissues snap, instantly halting the upward flow of hydrating sap, minerals, and complex nutrients. The commodity does not die immediately. It becomes a closed biological system forced to endure the physiological stress of separation. To maintain cellular integrity and survive, the severed organ must consume its own finite, unreplenishable carbohydrate reserves. This self-consumption is driven by aerobic respiration. The left side of the equation requires glucose and oxygen. Inside the produce, that glucose is strictly limited. The reaction yields carbon dioxide, water, and heat energy as ATP, adenosine triphosphate, the primary energy currency of cells. Every living agricultural commodity relies on this exact equation, but their baseline metabolic rates vary wildly. Nuts and dates maintain an extremely low basal respiration rate. Apples operate at a moderate pace. Asparagus and mushrooms, conversely, burn through their carbohydrates at a highly accelerated rate. Post-harvest shelf life is strictly and inversely proportional to this basal respiration rate. Since we cannot inject new nutrients into the harvested tissue, extending shelf life requires artificially restricting this biochemical equation. The oldest lever used to slow post-harvest decay is ambient temperature control. The thermal dynamics of post-harvest physiology are governed by the Hoff rule, specifically the Q10 temperature quotient. The math dictates that for every 10 degrees Celsius increase in ambient temperature, the rate of biochemical reactions inside the plant tissue doubles or triples. By actively cooling the produce, we systematically lower the kinetic energy of its cells. This loss of kinetic energy directly throttles the rate at which the fruit catabolizes its carbohydrates. But thermal engineering has a hard biological floor, known as chilling injury. Temperate crops like apples and pears can survive storage temperatures near 0 degrees Celsius. Tropical commodities suffer immediate cellular damage and quality defects if dropped below their 10 to 12 degree physiological threshold. Pushing chill-sensitive fruits too cold breaks down their cellular resistance to pathogens. Because thermal cooling has strict biological limits, preventing senescence requires chemical intervention. The plant kingdom utilizes two distinct evolutionary strategies for fruit maturation and decay. This graph plots carbon dioxide production over time. The dotted line tracks the non-climacteric pattern, where commodities like citrus experience a predictable decline. Conversely, the solid line maps the climacteric pattern in apples, requiring us to suppress a sudden, violent metabolic explosion. The specific biochemical trigger responsible for this climacteric spike is ethylene gas. Ethylene is an endogenous signaling hormone, synthesized internally via the ACC pathway when the fruit reaches maturity. It operates at potent trace concentrations of less than 0.1 microliters per liter. Once released, this hormone causes the rapid degradation of chlorophyll, stripping the green pigment from the skin. Structurally, it dissolves the rigid pectin in the cell walls, causing the fruit's tissue to soften and sag. Metabolically, it forces the rapid conversion of starches into simple sugars. Applying external ethylene to non-climacteric fruits simply accelerates their steady decline. It does not trigger a metabolic spike. For climacteric fruits, ethylene acts as the biological ignition switch for their own consumption. This process is driven by an autocatalytic reaction. The initial presence of ethylene triggers the fruit's tissues to rapidly synthesize even more ethylene, creating a compounding feedback loop. This loop rapidly exhausts the fruit's remaining carbohydrate and water reserves. If engineers fail to intercept this hormonal signal at the preclimacteric minimum, post-harvest senescence and total structural collapse are mathematically guaranteed. Controlled atmosphere, or CA storage, is the engineering solution used to break this autocatalytic loop. We can view aerobic respiration through Le Chatelier's principle. Changing the concentration of a chemical component shifts the system's equilibrium. By artificially reducing the ambient reactant, molecular oxygen, engineers force the chemical reaction to slow down. They simultaneously pump the ambient environment with excess product, specifically carbon dioxide. An abundance of external carbon dioxide creates back pressure against the equation, further stifling the fruit's ability to respire. Choking the respiration rate directly dampens the fruit's ability to synthesize endogenous ethylene. As a final safeguard, active chemical scrubbers are integrated into the storage environment to absorb any stray ethylene gas. This triple threat approach allows produce like apples to be stored for over a year without decaying. CA storage actively hacks the chemical environment to sever the fruit's hormonal communication. Atmospheric throttling has a fatal biological limit, known as the anaerobic threshold. Oxygen levels cannot be dropped to zero. If the environment dips below a critical 1 to 3% oxygen threshold, the cells abandon aerobic respiration entirely. The fruit shifts to fermentation, generating highly toxic acetaldehyde and ethanol that poison the tissue. Modern post-harvest preservation holds living tissue in a chemically engineered stasis, suspended just degrees above chilling injury and a single percentage point above anaerobic death.
Thank you. Disclaimer. Artificial intelligence, AI, was used in the development of selected instructional materials in this lesson. The use of AI is intended to enhance clarity, visualization, and learning engagement, while all academic content has been reviewed and guided by the instructor.